The modern web is built from layers of invisible machinery. A page appears on a screen. A button responds to a click. A balance changes inside a dashboard. To the user, the movement looks simple. Beneath the surface, however, software systems begin to exchange messages, verify rules, update records, and return a result. Web3 is not a separate internet. It is a different way of arranging identity, state, execution, and trust on top of the internet that already exists. The story begins with the original web. In 1989, Tim Berners-Lee proposed the World Wide Web at CERN as a system for linking information across computers. The early web was built around documents, links, browsers, and servers. A browser requested a page. A server returned it. The user read it. This structure is often described as Web 1.0. It was mostly a web of pages, static, readable, and comparatively simple. Then the web became interactive. Websites turned into platforms. Users created accounts, uploaded photos, sent messages, posted comments, watched videos, followed creators, and generated data with every session. This became Web 2.0. The architecture of Web 2.0 is familiar. At the top sits the front end, the visible part of the application. Behind it sits the back end, where server-side logic handles requests, permissions, recommendations, payments, moderation, and business rules. Beneath that sits the database, where accounts, posts, balances, messages, preferences, and private application state are stored. In this model, the platform is the center of authority. When a user logs in, the server checks an email, password, session token, phone number, or other credential. If the platform's database confirms the identity, access is granted. This system works well. It is fast to build, easy to update, and capable of serving enormous numbers of users. It also gives the platform direct control over the servers, the database, and the rules of access. Web3 changes this arrangement. It keeps the browser, the interface, and much of the ordinary internet infrastructure. But it moves selected parts of state and execution away from a private application database and onto a blockchain. A blockchain is a shared ledger maintained by a network of computers. These computers, commonly called nodes, keep track of the network and follow the protocol rules. In an ethereum-like system, the current state includes accounts, balances, deployed contract code, and contract storage. The transaction history lives in the chain of blocks that led to that state. This distinction matters. State is the present condition of the system. History is the sequence of transactions that produced it. In Web 2, the application database is usually private and controlled by one organization. In Web 3, part of the application state can be public, verifiable, and updated through a network protocol. The user's identity also changes shape. In a typical Web 2 application, identity begins with an account created on a platform. In Web 3, identity often begins with a wallet. A wallet is not merely a place where tokens are displayed. More precisely, it is software that manages cryptographic keys. The public address acts as a visible identifier. The private key proves control over that address. The private key should never be exposed. Instead, the wallet uses it to sign messages and transactions. This signature proves that a command came from the holder of the key, without revealing the key itself. This is the foundation of Web3 authentication. An application does not always need to store a password inside its own database. It can ask the wallet to sign a message. If the signature is valid, the application knows that the user controls the address. Reading from a blockchain is usually straightforward. A decentralized application can ask a node for information. The balance of an address, the owner of a token, the result of a smart contract function, or the current state of a protocol. This kind of read operation does not normally change the blockchain. It resembles asking a public database for information. Writing is different. Writing to a blockchain requires a transaction. A transaction is a signed instruction sent from an account to the network. It can transfer value, call a smart contract, deploy a new contract, or change contract state. The sequence is mechanical. First, the front end prepares the transaction data. This data may include the recipient address, the amount being sent, the smart contract function being called, and the encoded parameters for that function. Second, the wallet presents the transaction to the user. It may show the network, destination, estimated fee, and a summary of the action. Third, the user signs the transaction. The signature proves authorization. It does not mean the transaction has succeeded. It means the transaction is ready to be sent. Fourth, the signed transaction is broadcast to the network, often through an RPC node or infrastructure provider. RPC stands for Remote Procedure Call. In practice, it is a communication layer between the application and the blockchain network. The front end or back end sends a request to a node, and the node passes the transaction into the network. From there, the transaction enters the machinery of block production. On proof-of-stake networks, block proposers, builders, and validators participate in selecting, ordering, verifying, and finalizing transactions according to the rules of the protocol. Other blockchains may use different mechanisms, but the engineering pattern is similar. Transactions are checked, ordered, executed, and recorded. Once a transaction is included in a valid block and executed, the blockchain state is updated. Later finality gives that result stronger settlement assurance. This is where smart contracts become central. A smart contract is a program deployed to a blockchain address. It contains code, it can hold data, it can define functions, and it can execute when called by a transaction. A simple smart contract may store a number, transfer a token, check ownership, or emit an event. A more complex contract can manage lending, trading, governance, digital collectibles, access rights, or automated financial logic. The important detail is that the contract does not run on one private company server in the ordinary web 2 sense. Its execution is replicated and verified by the blockchain network according to shared rules. This makes smart contracts powerful, but also unforgiving. If a normal backend contains a bug, the developer can patch the server. If a smart contract contains a bug after deployment, repairing it may be difficult, expensive, or sometimes impossible, depending on how the contract was designed. For this reason, Web3 engineering places unusual weight on testing, auditing, upgrade patterns, access control, and careful contract design. A Web3 application is therefore not only a website, it is a stack. At the top is the front end, the visible interface built with ordinary web technologies. Beside it is the wallet, the user's key manager and signing tool. Below that is the RPC layer, the bridge between the application and blockchain nodes. Then comes the blockchain itself, the shared execution and settlement layer. Inside that layer, live accounts, transactions, blocks, and smart contracts. Around this core system, other services appear. Indexers collect blockchain data and organize it for fast search. This is necessary because blockchains are not always designed for convenient application queries. Reading raw chain data directly can be slow and awkward, especially for dashboards, histories, marketplaces, analytics, or governance interfaces. An indexer listens for contract events, processes chain data, and stores it in a query-friendly structure. This is why many Web3 apps still use servers and databases. The difference is that these services often support the interface, while the core ownership or settlement logic may remain on-chain. Storage creates another layer. Blockchains are expensive places to store large files. Images, videos, documents, and metadata are often stored off-chain using decentralized storage systems, conventional cloud storage, or hybrid approaches. The blockchain may store only a reference, a hash, or a pointer to that external data. Oracles add another piece to the machine. A blockchain by itself does not naturally know the outside world. It does not automatically know market prices, weather data, shipment status, sports results, or identity records. An oracle is a mechanism for bringing external data into the blockchain environment. It allows smart contracts to react to information that originates outside the chain. This is useful, but sensitive. If the data source is wrong, delayed, manipulated, or too centralized, the smart contract that depends on it can behave incorrectly. This is one of the central engineering tensions of Web3. On-chain execution can be transparent and verifiable, but the system still has to interact with off-chain reality. A complete Web3 application is a coordinated machine. The front end displays information. The wallet signs intent. The RPC node transmits requests. The blockchain orders and verifies transactions. The smart contract executes rules. The indexer prepares readable data. The storage layer holds larger files. The oracle brings in external data. Each layer solves one problem, and each layer introduces its own risks. This is why Web3 should not be reduced to coins, speculation, or slogans. Its more serious form is architectural. It changes where software keeps records. It changes how users prove identity. It changes how applications execute rules. It changes how digital ownership can be represented. But it does not remove complexity. It moves complexity into new places. Key management becomes critical. Smart contract security becomes critical. Interface design becomes critical. Fees, latency, scalability, indexing, storage, and data availability become engineering problems rather than marketing phrases. This is the practical reality of Web3. It is not magic placed on top of the internet. It problems rather than marketing phrases. This is the practical reality of Web3. It is not magic placed on top of the internet. It is a different distribution of responsibility across users, code, networks, and protocols. In Web 1.0, the browser mostly requested documents. In Web 2.0, the user interacted with platforms and private databases. In Web 3, the user can interact with public state, signed transactions, and programmable contracts. The visible action may still be a single click. Behind that click, a chain of systems begins to move. A wallet prepares a signature. A node receives a transaction. A network checks the rules. A contract executes code. A block records the result. An indexer updates the interface. And the application returns to the screen, appearing simple again. That simplicity is the illusion every well-designed system tries to create. The machinery remains beneath the surface, quiet, distributed, and precise.